Okay, so today we're going to be talking about star formation, and this one is this one's a little complicated. It's not intuitive. First off, you actually need to make sure you're using your ESRT. It has stuff in there about star formation, and you need to be taking notes along with me today. So the very first part of your assignment is going to look like one of the handouts that we currently have. So it's not the Google form; it's the Google Doc that you should be starting with. And so let's go through that. So at the top, it's just notes. So we're talking about a life cycle of a star. So very first definition. So a star is a massive object made of gas found in outer space that radiates electromagnetic radiation. So electromagnetic radiation falls under, or a lot of different things fall under that title, that heading. We'll go over that in a second. So Part 2, it says stars produce extremely great quantities of energy through the process of nuclear fusion. So the chemical formula is below. So on your sheet, you'll see how I put the formula down already. Um, and how we read this is 4 hydrogen atoms. And do you see at the bottom of that it says 100G? That means 100 grams. And then it has a little arrow with fusion above it. That's like the reaction. So this is a fusion reaction. So those 4 hydrogen atoms fuse together to form one helium. But if you notice below the helium, it says 99.3 grams. So there's a loss of 0.7 grams there. And it is in physics, like you say that nothing can be created or destroyed. So there is no just like it doesn't just disappear. It has to turn into something else. So what it turns into is energy, a massive amount of energy. So I know you guys seen videos before. I've shown them in class about like hydrogen bombs. So a fission bomb has that mushroom cloud look to it, and those are the atomic weapons that we used on Japan. But a hydrogen bomb is different. When they blow up, it usually looks like just a giant ball. And this is a fusion reaction, so it's the same thing. So there's fission reactions and fusion. So don't get those confused because they're very different things. Fission means to split. Fusion means to fuse together, like to pull together. Okay. So number 3, it says all stars have recognizable life cycles. The most important characteristic that will determine the type of life cycle a star will undergo is to look at the star's mass. And the reason why we look at a star's mass is because the larger the mass, the higher amount of gravity that star is able to generate. And so when the star has more and more gravity, it can pull things in tighter and tighter and cause fusion reactions to speed up. So that's very important. And I'll discuss why in a second. So we should be moving on to the second page of your note catcher that you're working on. The heading now should say star formation. So star formation, this is the process by which light elements join to make heavier elements. That's called nuclear fusion. We just went over this. So when they mean light elements, they mean things like hydrogen. So if you look at the periodic table of elements, you'll see hydrogen is on the top left-hand corner. It's the lightest element. So they're talking about these lighter elements, like those elements that are on the top row, combining together through nuclear fusion, which is like gravity pulling them so tight that they actually combine and release energy to form heavier elements. So like you could have a couple things forming together and forming carbon, and even diamond and stuff like that. Any of the heavier elements are caused through this nuclear fusion process. So the sun generates most of its energy by fusing hydrogen to make helium deep within the sun. So you're talking about like near the core of the sun, like these reactions are taking place. This loses almost 1% of mass during the process, and so that 1% loss is converted into energy. So however, nuclear fusion can only occur under extreme conditions of heat and pressure. So example, Jupiter is massive. It's very, very, very big, but it's still not it still doesn't have the gravity or let's say internal pressure to support fusion. So you can almost say that Jupiter is a failed star. It's a gas giant. It just never got big enough to actually start off nuclear fusion and to kick off being a small sun. So the first question that you have on this page is how does the sun get its energy? It's in the reading. and I just said it. So you should be able to fill this section out. These sections right here will be graded. It is easy to go through and just listen to what I just said, or you can just get it directly from the reading that you have. So, introduction to stars and nuclear fusion is the next page break. So, first off, we already started with this definition. A star is a massive object in space that creates energy and radiates it as electromagnetic radiation through a process called radiation. So a lot of people get this confused. They think of radiation as in like X-ray and stuff like that. When they're using the process called radiation, this means how energetic waves travel through matter. So this is the process of how it gets from one place to another. So it radiates out. So radiation can be, obviously, can cause cancer and stuff like that. Like I know that's what you're probably thinking when you think of radiation. But light, visible light, the light we see that's coming down right now, is a form of it radiates to get here. Okay. So if you compare the sun with thousands of stars known to astronomers, the sun appears to be a typical star. So we don't have a special star. It's not on the low end. It's not on the high end. It's just your average typical star. So actually, most stars that are visible in the night sky are larger and brighter than our own sun. So all the stars you see up there are actually, supergiants, red giants. We'll talk about the differentiations later. So at the same distances as the visible stars, there are more stars too dim to be visible from Earth. So what we see up there is not the true whole story. So how does the sun's energy reach the Earth? What is that process called? Radiation. So we're moving on to the next paragraph. So it says most of the mass of the sun is hydrogen, which is the lightest element. There is nothing lighter than hydrogen. As soon as you start splitting hydrogen in half, you're starting to get to those are not elements any longer. So when 4 hydrogen nuclei join to make a helium nucleus, they lose about 1% of their mass. During this process, light elements join to make heavier ones. That is the definition of nuclear fusion. So fission would be heavy elements like uranium and plutonium splitting and releasing energy through that split and forming lighter elements. So that's what a nuclear weapon is. So fusion is taking lighter elements, combining them, and that even releases energy and to form heavier elements. So while 1% may seem like a small loss of mass, it is enough to create a great amount of energy. However, nuclear fusion can only occur under extreme heat and pressure. So we have to state the formula again. So the formula that I gave you was a visual representation. So you're going to have to write it down. So you would write what you saw in the visual representation. You're going to write it in a sentence structure. Now we're on to the next paragraph. It says, once energy is created deep within the sun, it moves to the sun's visible surface by radiation and convection. So convection is the same process that carries heat within the Earth's interior. I think you guys probably remember we had something called convection cells, and it showed those circular, something would heat up, and when it heats up, it expands and becomes less dense. And when something is less dense, it rises towards the Earth's surface. And then once it's up there, it cools down, shrinks, becomes more dense, and sinks again. So this is the same exact process that happens in the sun. So they have convection cells inside the sun. So from the solar surface, the energy escapes as electromagnetic radiation, or radiation, that term that you've heard before. So the surface temperature of the star determines the kind of electromagnetic radiation or electromagnetic energy it radiates into space. The sun is a yellow star because it's roughly about 6,000 degrees Celsius on its surface, and so it radiates most intensely as yellow light in the visible part of the spectrum. So we're on Introduction to Star Formation section now. So star formation. So a star begins basically in what they call stellar nurseries. It's these giant, vast areas of space that have a whole bunch of gas there. And as time goes on, these molecules, every single thing in the entire universe has its own gravity field. Even you do. Like, you're attracted to something else. Heavier, denser things have more pull on you. But it requires a mass amount of it to gather together to actually create something that we can feel. Even our moon, it has a gravity field of its own. That's what causes the tides. It actually pulls the water up and off the Earth's surface. So we're talking about these giant gas fields that eventually start to coalesce, and all the gas starts pulling more and more together. And as more of it flies together, it has a greater and greater gravity field, and it pulls more and more in. So mostly hydrogen. Okay, so it begins to draw them in together. So some of it's hydrogen and helium that are left over from the universe, basically. So the Big Bang, so 14 billion years old. The rest of the debris from the explosions of massive stars that had formed earlier. So there's tons of debris out there from stars that have exploded, and they shot their material all over the place, and then those coalesce once again back into stars. So this initial phase takes place over a period of 50 million years. Like I said, it's a very slow process, but the larger the star, the faster the process. So going on, you guys can answer that question. It says, what force causes gas and dust to clump together? So we're going on down to the next part. So it says, as a material draws closer, heat from the collapse of matter and from friction cause the temperature to increase until there's enough heat and pressure to support nuclear fusion. So at this time, the star becomes easily visible since it produces and radiates great quantities of energy, like in the form of heat and light. So the star becomes less luminous after it finally condenses and spends most of its life as something called a main sequence star. This is the main sequence star is a phase of the star's life. So our sun is currently in this stage, main sequence star. That term will come up fairly often, probably on the regents. So gravitational pressure balanced by heat from nuclear fusion prevents the star from further shrinkage. So like we have gravity is pulling everything in, but the heat of nuclear fusion inside is pushing out. So that it creates a balance to prevent the star from collapsing even further and further in. Okay, so if it collapsed further and further in, it could explode or turn into a black hole. So we'll talk about that in the future. So this is the longest and most stable phase of stellar evolution. So we can go down to the next reading paragraph. It says, after about 10 billion years, a star the size of the sun runs low on hydrogen. So it's basically running out of fuel. It's like in your car, you have a certain amount of gas in the tank, and as soon as you run out, it's going to stop. So the sun can't go refuel itself. That's not a thing. So we're going to talk about the end of the life cycle. So fusion slows down, and the core of helium collapses. So like I said, once the fusion starts slowing down, there's not a lot of heat to press out anymore. And so the star will start collapsing back into itself. This causes the outer part so when the helium core collapses in on itself, this causes the outer part of the star to quickly expand out. And this is what causes a red dwarf. So you can think of the inner core collapsing in on itself, and this gaseous part on the outside, which is called the outer core, or outer part of the star, expands out, and forms a red giant. So the fusion of helium and other heavier elements that are happening inside replaces the hydrogen fusion process. So now big heavy elements are starting to form in this center part of the sun. And the outer shell of gases expands and cools. And so this is the red giant stage, and this is where, when our sun goes through this is where the sun looks like it's expanding out towards us. That's just the outer shell expanding out, and it would burn all the inner planets up, including the Earth. Like we would be just swallowed up by the sun. So the outer shell of gases expands out, cools, the red giant phase, but it leaves behind, in the center, a hot core, which is called a white dwarf. So our sun would leave a white dwarf, like left over. Finally, we have two more paragraphs. So stars with more than 10 times the amount of our sun end their period of the main sequence more violently. So ours is going to end, by burning up all the inner planets in our solar system, but other stars that are 10 times larger blow up. Okay, so these stars form a variety of heavier elements. So these stars are so big that they can form like everything. You're thinking plutonium, uranium, all that. They produce a lot of crazy stuff. So the collapse of the process of larger stars generates so much energy that they end their life in an explosion called a supernova. So they briefly generate more energy than billions of stars that make up the entire galaxy. So one supernova will release as much energy or more than every single star that is just going about its normal life at that single moment. So most of the mass of the star is blown into outer space. So after a supernova, the core may form an extremely dense object called a neutron star. So this is like something that's extraordinarily small. And you can basically say a neutron star. I believe the old like saying was, and this is like 25 years ago, is like a teaspoonful of the material that makes up a neutron star would weigh more than the entire Earth. It would be denser than the entire Earth and way more, which is like insane. So some stars are so massive that they form an object with a gravity so strong that not even light can escape. And this is what a black hole is. So black holes cannot radiate energy. They don't give off energy because everything is sucked into the center. So, but they can be detected because the energy giving off of matter that falls into them. So if it ever captures anything, there's some stray pieces of energy that are being given off, and that's what we can see, them being actually sucked in before it all goes dark. They can also be located by their gravitational effects on other objects. So they're so massive, they cause everything around it to distort and warp and like whatever like formation. If it's going in a circle, it will actually pull in or distort the circle, cause it to be more oblique. Just different things. Okay, so that's it. The last thing that I left you with on here is the life cycle of the star. So you can see this. It says stellar nebula. Then it goes to average star, which is what we are. So after we're average star, we'll go to red giant. Then they'll be left over with just a nebula again and just a white dwarf. And so that's what our star's heading towards. Now you can look at the other track, which is like massive star, red supergiant, supernova, which will either form a black hole or a neutron star. And so that is it. And you have a section of regents questions on there. Remember, you need to probably use your ESRT. It has the life cycle of the star in there, or you can use these notes as well.